All right, hello everyone. So today I'm going to give my presentation on the seismic performance of smooth reinforcing bars and reinforced concrete columns. So before I get started, I just wanted to talk a little bit about the motivation or what brought us to smooth reinforcing bars. All right, so what started was the use of using grade 80 steel in members that form plastic hinges. So these are members that are in seismic regions. And so specifically the codes such as the California Seismic Design Criteria prevents the use of grade 80 steel in members that form plastic hinges. Additionally, in other states such as Oregon, Washington, and AASHTO specify on that you cannot use grade 80 steel until further research becomes available on how it performs in seismic regions. So to use grade 80 steel is really beneficial because higher strength steel can lead to things like more efficient designs, which can reduce congestion and improve confinement. So this can be really important in really high seismic regions where you have a lot of steel and like things like places like California where you have 26,000 bridges, it can really make a difference in the bridge construction. It can reduce construction costs, time, and improve scheduling. So why is grade 80 steel restricted in members that form plastic hinges? So as you can see on the graph on the right, you can see that as the steel increases strength, the maximum elongation starts to reduce. So as we go from 40 to 60 to 80 to 100, we lose the uniform elongation. In fact, grade 80 steel is 33%, has 33% less uniform elongation compared to grade 60 steel. And so from that, we started our research on conducting on grade 80 steel by conducting 4 large-scale reverse cyclic column tests that are reinforced with grade 80 steel. So these were conducted to try to see how the grade 80 steel would perform seismically, and then see what the differences are between the grade 80 and the grade 60 steel. So the main differences that we found is that the grade 80 steel in these tests had lower displacement capacity, and they had smaller post-buckling cycles until fracture. What I mean by that is if you look at the grade 60, you can see the circle, and between the circle is when the bar buckles to when it fractures, which is the X. We have 3 cycles between when those limit states happened. And if we look at the grade 80 steel, we had only 1 cycle between when the bar buckled, the circle, versus the X, which is when the bar fractured. So knowing those differences, we wanted to further investigate what was happening between in the grade 80 bars. So what we did, we attributed what the difference was. So we were thinking that this might be due to the bar buckling. So the idea is that the differences might be due to this bending strain capacity. So if we buckle our bar significantly enough in compression, we'll start to form these cracks that you can see here between the ribs. And so if we buckle our bar enough that in compression, these bars will end up fracturing at tension. So this is what causes the bar to fracture after the bar is buckled. So to kind of see what this theory is, we were looking at calculating this bending strain capacity for grade 60 columns and grade 80 columns. And what we can find is that when we look at these 2 graphs, so each of the black dots or black squares are representative of different cycles in our test. And then the red X is representative of the maximum strain before the bar fractures. So as you can see, each of these lines is a different bar, and we can see that the red X's where the max strain before the bar fractures kind of align in a similar range. So we can call that the range of critical bending strain. So you can see that for grade 60 columns, this range of critical bending strain. And then we can look at the grade 80 columns, and we can see that this is much lower for the 2 types of steel. You can see that the grade 60 columns ended up being about 0.13 to 0.16 critical bending strain, that range that you see there, versus 0.909 versus 0.1. So this is kind of what we might be attributing to the differences between the grade 60 and the grade 80 steel. So to understand this, and without having to build more columns immediately, we developed a test at NCSU called the buckle bar tension test. So this is kind of to replicate the reverse tension and compression loading of a longitudinal bar during a cyclic column test. So the idea is that we have a rebar specimen that's straight, and then we apply a compressive load onto the bar to simulate this compression loading during an earthquake, and then we pull it in tension. And what we'll see that if we buckle the bar to a high enough curvature, the bar will experience a brittle failure when it's pulled in tension. So those cracks that we saw earlier start to form. And so we can see the differences between the red and the black. So the red being a non-ductile or brittle failure versus the ductile black line that you see there. So with this BBT test, we decided to look further into more types of steel. So still grade 80 steel, we decided to look at the steel that was used to reinforce the columns that we just saw. So the grade 80 and the grade 60 columns that we're comparing. So we conducted this material test on this column steel, and we can see, we can plot the axial strain at max stress versus the maximum bending. And we can see kind of the range where that bending strain starts to drop off. So we can also call this the critical bending strain, this range in the pink you see here. We can see that for grade 60 or for grade 80, it's still lower in the black versus the red diamonds that are the grade 60. And then we can look at the results of this range for column test. And we can see that they were pretty similar. These ranges that we see here are pretty similar to the column test results, so from the material testing results. So we found that this BBT test results could be some type of indication of column performance, meaning that we can try to test some types of rebar first to see how it'll behave, and it can kind of give us an idea how it might behave on a large scale, global scale in a reinforced concrete column. So we conducted different BBT tests on different types of grade 80 steel. And one of the ones that I'm going to show is related to the smooth bar that I'm going to look at. But one of the ones that we found is that the mill one that's shown here is from the column test that we saw that had a lower displacement capacity and also fewer cycles between bar buckling and fracture. And mill 2 is a different type of steel that we looked at. And you can see the difference between the two are that mill 2 has a larger radii. So the radius of mill 1 versus mill 2 is much larger. And we found that the performance of the mill 1 versus mill 2, so the mill 1 is in black and the mill 2 is in blue, we can see that we're able to get a higher bending strain capacity for our mill 2 rebar. So that if that's indicative of how it might perform on a column level, we thought that mill 2 would perform better for compared to the mill 1. So the next step was to do a column test on it. So we've done several column tests on this mill 2 steel, and I'm just going to show the results of one. But we can look at the mill 2 grade 80 column, and we can find that first we can look at the grade 60, and we can compare the grade 80 column test to the grade 60, and actually the grade 80 column test was able to exceed the displacement capacity of the grade 60 columns, meaning that we could push it further. And so we can look at the force displacement. So the grade 80 column test made it to ductility 7 versus the grade 60 column only made it to ductility 6. If we look at the displacement history, we also found that the first fracture for the grade 80 column occurred later. In ductility 7 versus ductility 6. So you can see that maybe the BBT test can represent indicative of some of the performance of the actual column. So the next thing we wanted to do is, so these rebar geometries impacted the performance. So we thought, why don't we take off the ribs? So we decided to do BBT tests without any ribs on the bars. So we looked at smooth bars, and we can see first what I have in the red and the black are grade 80 bars with ribs, so our traditional rebar. And then when we looked at the results from the bars without ribs in the BBT test, you can see how much more bending strain capacity that we got from the test. So so we were able to increase our bending strain capacity by just removing these ribs that were causing a strain concentration when we were buckling and compression, and that was causing it to not be able to be bent more significantly. So knowing these results, the next step was to try to come up with to try to test it on a column scale. So that's what I'm going to be discussing next, is we decided to do 2 large-scale reverse cyclic column tests that are reinforced with grade 80 steel. So they had unconventional detailing. So these columns were 8 foot tall. They had an axial load of 15%. And we decided to do 2 different tests. One that had a smooth bar completely that's headed, and the other one that had a smooth bar just in the plastic hinge region, and the rest had ribs on it. So we were able to have these 2 tests, and we were able to have comparison grade 60 tests that have matched strength. So instead of we're matching the strength. So instead of using a number 8 grade 80 or grade 60 bar, we're using a number 7. And then we also have comparison columns that have traditional ribs on them. So we have a lot of comparisons to these 2 types of tests. So the 2 different ways that these rebars are made is, the first one is a smooth headed bar. So the main purpose of this bar is that it's just really easy to construct and implement in practice. So there's not a coupler that you have to couple to it. We actually use the base material. So this is the base steel before it becomes rolled at the mill. And then, so this will allow for easier constructability, easier manufacturing. And the next one is the smooth bar in the plastic hinge region only. So we have a smooth headed bar, and then we couple that to a ribbed, or traditional ribbed bar. So this is to be able to give us some of the friction bond that outside of the plastic hinge region. So next we go to construct our columns. So we start out by tying all of our steel. We start by tying our footing steel, casting our footing. And what you can see, the pink foam here, is that we block out our steel or the concrete cover so that we can instrument the rebar. And so the limit states that we're looking at, the concrete cover is already gone at buckling and fracture of the bar. So we block it out so we can get better data of the results. And then we cast our columns, and then we have our columns here. So these tests were actually completed this month, and I'm going to go over some of the results and how we do the tests. So the columns that we have are subject to a quasi-static unidirectional 3-cycle loading. So we have at our lab a 220 kip actuator where we push and pull our column to simulate this earthquake loading. We have a spreader beam that applies a constant axial load onto our column to simulate the dead load of a bridge. And then we post tension our footing to the strong floor so it doesn't move. And then, as I mentioned, we have our 3D optical LED positioning of our columns in this instrumented region to be able to get the strain data for longitudinal and transverse steel of our column. And some things we kept the same is that we had the exact same loading history for all of the comparison columns that I'm going to be showing. So the difference is that the ductility values might be slightly different because the smooth bars were slightly stronger. They hadn't had their ribs put on them. And then the axial load is the same exact axial load, but the axial load percentage might be slightly different due to differences in concrete strength. So this way we can be able to facilitate a comparison of the columns in a more meaningful way and maintain the exact load and energy comparison. So the 3 tests that I'll show is the column test will be the same exact detailing I showed. One will be with ribs. So this is the final results of the test. One that has a smooth headed bar that I mentioned, and then one is the smooth bar in the plastic hinge region. So I'm just going to cover the force displacement results of each of these tests. So we can start first by looking at these smooth headed bars. So what we found for the smooth headed bar, so this is the bar with ribs. And if we plot the smooth headed bars on the column, we can notice a few things. So the main thing we found was that the bar was slipping a lot because it had no ribs it only had the chemical bond between the steel and the concrete. So it had no ribs, so it was slipping significantly. So we ended up having to end the test early by a failure mode that I'll show on the next slide. But another thing we can note is that we have less energy dissipated. We can see the loops are a little bit more pinched in the middle here. So that's due mainly to the slipping of the rebar during the test. So the test concluded, we got to ductility 6, but what really happened before we got to ductility 6, right before that, is we had a failure mode that isn't typical we usually see. We usually buckle the bar and then fracture the bar. And so what we ended up seeing with this test is that we had punch out of the 10-foot long bar into the cap beam because we had a significant amount of slip. So we didn't specifically detail our columns for a punch out failure at the top. These are 10-foot long bars. So we mostly detail our gap beams to be capacity protected for the actuator load. So this is what the end result of the failure mode that we had that was not typical of a typical reinforced column. So we didn't end up buckling or fracturing any bars. We had punch out failure through the top of the cap beam here. So the next test we can look at is the rebar width ribs. So this can kind of give us some of the bond that we were missing for our smooth bar. So this test actually has fairly similar behavior to our traditional rebar width ribs. So we have our smooth bar on the plastic hinge and the behavior is fairly similar, but the really important thing to note is that we had many cycles after the bar buckled until it fractured. So that gives us time between those two limit states to be able to have a little bit capacity after bar buckling occurs. And so they definitely, you can see that their results are fairly similar for those two types of tests. And then the other thing that we found for both of the tests was that we had a minimized splitting damage compared to the traditional reinforcing steel. So what we can look, when we compare the two tests, we are smooth headed bars on the left and our smooth bar and plastic hinge on the right. And this can really show you guys what I'm talking about when the bar slipped. So you can see the reinforcing steel, and this video is on loop, but you can see the reinforcing steel on the smooth headed bar. You can see that everything is moving. The spirals in the concrete are sliding along that bar, versus the smooth bar on the plastic hinge was not slipping as much and was able to buckle and fracture as we expect. So what we found was that the smooth headed bar specifically slipped at almost 2 inches. That bar was slipping back and forth. So enough so that it was knocking off some of those optical sensors that are on the rebar. So the final things that we can say from these two tests that we did is that unconventional detailing, such as smooth bar and the plastic hinge, was able to match or be comparable to the ribbed traditional columns, but further detailing is required for the smooth bars to implement that. Because it punched through, we need to detail the top of the cap beam, provide more reinforcing to the top or a plate on top to prevent that punch out failure. So the future of this research is more tests. So we plan on doing, along with some more grade 80 tests, but we plan on looking at shake table tests to kind of simulate this type of seismic loading. So we already have the bars ready for that. So that's it for my presentation. I'm happy to answer any questions on it. Yeah.
Thank you, Jessi, for the presentation.